All right, section 4.6 you are familiar with. It's talking about complex numbers. I'm going to expand a little bit on your complex number knowledge. So we're going to have a little bit of fun with the number I, and then we're also going to explore division with complex numbers. So first I want you to think about what I is. You know off to the side here, because we've talked about this already, that I is the square root of -1. Okay, so I want you to build on this. Now you already know what I squared is, probably from watching previous videos from section 4.6, but thinking about if I square I, that means I'm going to, so if I square I'm going to square the square root of -1. Well, you know when you square a square root, that cancels out. So I squared is really just a real number. Okay, so you start with I to the first is I, right? I should put that there, sorry. I squared is -1. Well, I cubed, if I keep going, I cubed is the product of I squared times I to the first, right? Well, now I know I squared is -1, and -1 times I is -I. So that means I cubed is a negative I. Keep going. I to the fourth. Well, I to the fourth is a product of I cubed times I, or I squared times I squared. I'm going to go that route because that's easier. I squared is -1. I squared is -1, and -1 times -1 is +1. Well, what's going to happen when you do I to the fifth? Well, I to the fifth is the product of I to the fourth times I. Well, I already know I to the fourth is 1, and 1 times I is I. Well, you probably get it at this point that it's going to start repeating. So my pattern was I, -1, I, 1. Now it's going back to I, so that means I to the 6th will be -1. I to the 7th will be -I. I to the 8th is 1. Now you can double check any of these if you don't believe me. So it's going to repeat this pattern over and over and over again. So what if I wanted to know what I to the 87th is? Well, I don't obviously want to lay this out until I get to 87, but I know it's a pattern of fours. Every fourth number is one of these values. So if I just take 87 and divide it by 4, that goes in there twice. 4 goes into 7 once with 3 left over, so I have 21 and 3/4. Not that you had to do long division for that, but this 3/4 means that out of the 4 numbers in the pattern, I to the 87th is going to be the third one. So that means it's going to be -I, and that's just kind of a cool, clever way. Now, if you type these on your calculator, by the way, and your I button on your calculator is above your decimal, check it out for sure. It's a nice checking mechanism. If you type I squared on your calculator, it's going to tell you -1. If you type in I to the 5th on your calculator, it's going to tell you I. Now, what it's not going to do is if you try to do, I to the 87th, it's probably going to give you something a little bit crazy, and it's not going to necessarily, once it gets too high, your calculator just starts going nuts. So, something cool. All right, now I'm going to move on to division of complex numbers. But before I do that, you need to know that you're going to be using a concept called complex conjugates. And two numbers are complex conjugates if their imaginary pieces are opposite signs. So notice a plus bi and a minus bi, so the imaginary parts are plus and minus. So for example, if I had 5 plus 2i, what would its conjugate be? Well, its conjugate would be 5 minus 2i, and those are conjugates of one another. So again, the imaginary part is opposite sign. If you had just 2i, its conjugate is -2i. There is no real part to it. So that's what a complex conjugate is. Pretty simple. Now, here's why you're going to use it. When you divide complex numbers, Okay, and I want you to put a little star here. When you divide complex numbers, you cannot have imaginary numbers in the denominator. Okay, so you absolutely cannot have imaginary numbers in your denominator. So looking at this, 6 plus 4i divided by 2 plus I have imaginary numbers in my denominator. Okay, so what's going to take care of that? Well, if you recall complex conjugates, if you FOIL out complex conjugates, your inner and your outer terms are always going to wipe each other out. And you're going to see that, and hence it's going to wipe out the imaginary numbers in your denominator. Okay, so the process that's involved here is a little bit lengthy, but it's definitely not challenging. So what you're going to do is you're going to take the original problem, and you're going to multiply both the numerator and the denominator by the complex conjugate of the denominator. So 2 plus I, its conjugate is 2 minus I, right? Change the sign of the imaginary part. So I'm going to take the top times 2 minus I, numerator and the denominator, times 2 minus I. And what is 2 minus I divided by 2 minus I? It's really just 1. So I'm just taking this fraction times 1, which is totally legal. Okay, so balance it out, right? Now I need to FOIL this bad boy out. So if I FOIL the numerator, I'll do this slowly for the first one. 6 times 2 is 12. 6 times negative I is minus 6i. 4i times 2 is plus 8i. 4i times negative I is minus 4i squared. The denominator I'll FOIL out. 2 times 2 is 4. 2 times negative I times positive 2, and I times negative I is negative I squared. Okay, now I can combine a few like terms for sure. 12 negative 6 plus 8i would be plus 2i. In my denominator, negative 2i plus 2i, that cancels out, so that's good. So a little bit of simplifying. Now the other thing you need to note, of course, is I squared. I squared is what again? It's negative 1. So this negative 4 times I squared is really a positive 4. This negative I squared is really a positive 1. Okay, so I'm going to scooch this up here. So that means my numerator is really 12 plus 2i plus 4. My denominator is really 4 plus 1. So now I can combine terms again. 12 plus 4 is 16 plus 2i, and my denominator 4 plus 1 is 5. Now last but not least, you need to double check if you write these as individual fractions, 16 fifths plus 2 fifths I. Nothing reduces, but it's a good thing to check. Now your question might be, could I leave my answer like this? And I would say absolutely yes, but if any of these pieces individually reduced, I'm going to get you for that. Alright, I'm going to go through this one a little more quickly. Why don't you pause the video and try to do it on your own, but I'm going to, like I said, go through it quickly. One thing I want to do before I work through it, however, is let you know how you can figure out this answer on your calculator. So if you, first of all, it's a quantity, so if you put these in parentheses and type this in exactly like it is on your calculator, remember your I is above your decimal, your calculator is going to give you the answer. And that is so very cool. But I want you to also understand on your exam, you're going to have to do these without your graphing calculator. Okay, so check it. It's a nice checking mechanism for sure, especially for your homework. Please make sure you can do these by hand. All right, now I'm going to go through this one kind of quick. So I cannot have imaginary numbers in the denominator. So the complex conjugate of 3 plus 3i would be 3 minus 3i. So I have to multiply the numerator by 3 minus 3i to balance. Okay, so I'm going to FOIL the numerator first. So 8 times 3 is 24. 8 minus 3i is minus 24i. 4 times 3 is minus 12i. Negative 4 times negative 3 is plus 12i squared. Denominator, 3 times 3 is 9, minus 9i, plus 9i. minus 9i squared. That's a lot of 9s. Woo. All right, then I'm going to do a couple things at once because I think you can handle this. I squared is a negative 1, so this value is really negative 12. I squared is a negative 1, so this is really plus 9. So I'm going to have 24. This combines to negative 36i minus 12. In the denominator, my 9 i's wipe out, so I really have 9 plus 9. So that is, combining my like terms, 24 minus 12 is 12, minus 36i, 9 plus 9 is 18. Now, here is where I would highly recommend that you separate things, or just note that 12, 36, and 18 are all divisible by 6, but I'm going to write these as individual fractions. So 12 18ths, of course, they both are, again, divisible by 6, so that's really 2/3. And 36 18ths is really, they're both divisible by 9. Or, excuse me, gosh, I wrote down the wrong number here. Oh, I can't erase it. Okay, so I'm just going to scribble through this. 36 divided by 18 is 2, so it's 2/3. Minus 2i. Why did I start changing that to plus there? Oof, lots of yucky mistakes here. I'll just toss in a negative, right? So the one thing you want, besides my lousy mistakes, sorry, is to make sure that you reduce everything. So if you did here divide everything by 6, because that's the only thing that goes into everything, you're not going to quite get here, although hopefully you would eventually see it. So I would separate them and write that final answer.